Unit 4 Chemistry, Chapter 12, Part 4. Now looking still at PROTON NMR, but what is called high resolution PROTON NMR. Okay, so this is based on the fact that in any molecule there are lots and lots and lots of hydrogens, and they affect each other a little if they're in different environments. So those peaks we were looking at before for the hydrogen NMR, we can zoom in on them to make what's called high res. And what we'll see is several smaller peaks in there. And it's due to what's called spin-spin coupling, okay? Which means the influence of the adjacent hydrogen in different environments causing a slight variation in their chemical shift. Okay? Our rule is the n+1 rule. Okay? If we have n protons as its nearest neighbour, its peak is going to split into n+1. Okay? So if I have 2 protons next to me in a different environment, my peak is going to split into 2 + 1, which makes 3. Okay? The reason. If I've got no adjacent hydrogens, then there's no effect, so I'm just going to be one peak, called a singlet. But if I've got an adjacent one, just one adjacent to me, then I can either align in the same direction as that one, or opposite to that one that's next to me. And those two probabilities are equally likely. So one adjacent hydrogen, I can either be with it or against it. It means I've got 2 possibilities, so I'm going to split into 2. It's going to give me 2 lines, which will be a doublet. Okay? As we start adding more adjacent hydrogens, the number of possible combinations increases. So if I've got 2, I can either be with both of them, or with one and against one, or with the other one and against the other one, or against both of them. Okay? Don't worry too much about how it's worked out, just this is where we get from. Okay? So here we'd get a triplet, and our middle line is going to be twice as high than the ones on either side. So if we go back to ethanol, okay? Ethanol, remember, had 3 environments, and we can still see that, because none of the information from our low res has disappeared, and we're still using that. So I've got 3 environments. 1, 2, 3. Okay? I've still got a relative peak area of 3 to 2 to 1. Okay? And that's still telling me how many environments are in each group which is causing that peak. But I've also got the information from my splitting. So this one, which is caused by a CH3, that CH3 is adjacent to a CH2. Okay? CH2 obviously has 2 hydrogens in it. So that is causing this peak here to split into 2 + 1, so it's split into a triplet. 1, 2, 3. Okay? My CH2 still has a relative area of 2, still in the place where we'd expect it. It has got 3 hydrogens in a different environment next to it, so it's split into 1, 2, 3, 4. Now I know what you're thinking. Hang on a minute, hasn't it got a hydrogen in an OH group next to it as well? Yeah, it's just what you were thinking, wasn't it? It does, but splitting does not occur across an oxygen. So in OH groups, whether they're in acid or alkanols, you do not get splitting across an oxygen due to it being exceedingly electronegative. Okay? It's like an oxygen force field. Okay? So anytime you've got an OH group in an acid or an alkanol, it's always going to be a singlet, and it's never going to cause splitting in ones that are next to it.